So hello everyone, welcome back. In this video, we will learn about eigenvalues and eigenvectors. So let's say we have a n cross n matrix, which is n rows and n columns. And we have, let's say, scalars lambda, which are basically numbers, and let's say we have vectors x which aren't zero, which that is, we don't have a zero vector, but they're basically non-zero elements. So if they satisfy the following equation, which is mx equals lambda x, where x are the vectors here and scalars lambda. If they satisfy this equation, then we call these x's, which are vectors, we call them eigenvectors of m, and these lambdas are eigenvalues of m. So you can think of it like this: you have a vector x. When you act by a matrix, you can think of matrices as operators or something like that. So if you act a matrix m on a vector x, you translate it by a number lambda. That is, you move it or you multiply it by a number lambda. This is an intuitive way to think about eigenvalues and eigenvectors, or this equation basically. So if you multiply by a matrix, you basically scale the vector. The scalar can be 2, 3, 4, or whatever that is, but you scale the vector. That is the most important thing. So the important question here is, we now know there's this relation which can be satisfied by the vectors. So the question is, how do we find these? I will use these shorthand notations: eigenvectors and corresponding to any matrix M. How do you find them? So let's start with the equation. So equation here is mx equals lambda x. If we take the lambda to this side, we have to write it like this: equals 0, or I can take stuff like this. So yeah, so note that this equation implies either this is 0 or this, right? But as we mentioned earlier, the vectors can't be 0, so this part should be 0. That is, we say that the determinant of m minus lambda I should be 0, as x not equal 0. Okay, so let's now try to calculate the eigenvectors and eigenvalues. Let's start with, let's say, the matrix, a 2 by 2 matrix, our usual example. Let's see if we have an example. Or okay, let's say we have these elements a12, a21, a22. So m minus lambda I would be something like this: minus lambda I. Okay, let's be more specific. It's the identity matrix in 2 dimensions, if you're wondering what I is. So let's pick some specific example. Let's say m is equal to this thing, 5 minus 2. So what is m minus lambda I here? This is 7 minus lambda minus 4, 5 minus 2 minus lambda. So the determinant of this is, if you simplify it, it will take this form, and we call this thing the characteristic polynomial. The naming isn't important, but if you want to know it, so that for that I've written it. So it's called the characteristic polynomial, and since the determinant is 0, we can set the characteristic polynomial to 0, that is plus 6 equal to 0. We then call this a characteristic equation, and if we do some factorization, we get something like this. So the allowed values of lambda is 2 and 3. So for lambda equals 2, we have 7 minus lambda minus 4, 5 2 minus lambda. Let's break the vectors. Since we're dealing in 2 dimensions or 2 cross 2 matrices, let's write the vectors as something like this: s1, x1, x2. This equation is basically, if you're wondering what this is basically a minus lambda I x equals 0. So this is basically this. Okay, so if you plug the value of lambda here, which is 2, we have 5 minus 4, 5 minus 4 again, and x1, x2 equals 0. So we have two. So some of you are pretty sure familiar with this. You have 2 equations. You can break them down and write a system of linear equations. If you break them down, we have something like this. We have 2 equations, which is, they're basically the same. That is 5x1 minus 4x2 equals 0, 5x1 minus 4x2 equal to 0. So they're basically the same equation. So x1 equals 4 over 5x2. So we don't have a specific value of x2, and x2 is basically free. It can be any number. So if it is free, since it can be any number, let's say x2 equals alpha, where alpha is any number you can imagine. So x equals 4 over 5, the vector. Obviously I should have used a vector sign, but since it's obvious here, I've avoided it. So you have something like this. The x2 is alpha. If x2 is alpha, your x1 is 4 over 5 alpha. This is the eigenvector corresponding to lambda 2. So you can write it, we'll often use this notation to write it: 4 over 5 transpose. So the eigenvectors are all non-zero multiples of this. We will often use this notation. We can write alpha here if you want, but if you want to say that our eigenvector is a non-zero, our eigenvector is a non-zero multiple of this 4 over 5, this vector, you can write it like this as well. So there is that. And for lambda equals 3, you can follow a similar procedure, and you'll find this, where beta is again any number. So you have your 2 eigenvectors here. Yeah, so this sums up our procedure for finding the eigenvalue and eigenvector of a matrix M. So what do we do? let's just summarize in a bit. So we first develop the characteristic polynomial, that is, and go to the characteristic equation. We find the eigenvalues, plug them into our equation, and ultimately we get the eigenvectors. Now we are done with eigenvalues and eigenvectors. Let's proceed to something called, let's go to the next page, diagonalization of a matrix. I'm introducing it in this section because diagonalization uses the idea of eigenvalues and eigenvectors. So there's a lemma. I'll write it like this. So if you have a real matrix, let's say n cross n matrix, that's better. So a real n cross n matrix and let's say lambda 1, lambda n are the eigenvalues. I'm writing the shorthand notation. This means eigenvalues if you're confused. So v1, vn are the eigenvectors, vectors of our matrix A, and we have a matrix C, which is formed, C matrix formed, let's write it like this, C matrix formed by vectors, say Vj from the jth column. This will become clear in a bit. And D, the diagonal matrix whose entries are lambda. So if we have these things, we can write an equation like this, which is AC CD, where A is our matrix whose eigenvalues are like this, C is a matrix formed by these vectors, which is our eigenvectors, and D is a diagonal matrix whose entries are our eigenvalues. So if we have such criteria satisfied by these matrices, then we can write an equation like this. Let's see a small sketch of the proof, and we'll come back shortly to why this is relevant to our discussion. So let's say we have a matrix C with our eigenvectors. So if we multiply it, so AV1, AVN, there's that, and the right hand side D is our diagonal matrix, which this is C, this is D. Then we have so what does this imply? The left hand side and right hand side implies, if you match the terms, AV1 is lambda 1 V1 and AVN is lambda n Vn, which is our eigenvalue equation, right? So AC, if this holds, if a vector is actually an eigenvector and lambda is the eigenvalue, then we can say AC equals CD, where A is the matrix we're dealing with, C is a matrix formed by our eigenvectors, and D is a matrix formed with our eigenvalues. It's a diagonal matrix whose entries are the eigenvalues of our matrix A. So the equation is satisfied. So important thing to note, if C is invertible, then we can write D equals C inverse AC. That is, we know a procedure to diagonalize a matrix. How? Because if we have A and if we know the eigenvectors of A, we can construct the matrix C, find its inverse, and then we can have a diagonal matrix which corresponds to our original matrix A. This is the process of diagonalization. Of a matrix. Okay, so let's see an example of how things are done on this side. Let's say you have a matrix A with entries like this. If you want to find the eigenvalues, you'll get it something like this. And lambda equals 2 and minus 1. Eigenvectors is x1. R is again any number. So x2 is r minus 2, 1. So the important thing, the reason why I wanted to show the example is how do you construct the matrix C. You guys might be confused about how to construct the matrix. So if we constructing C matrix, how do you do that? You just take these eigenvectors. Let's say you can take r equal to 1, since since you have the freedom to take any r would satisfy the relationship, the eigenvector relationship. So if you pick a value of r, let's say for simplicity we pick 1, we can construct the C matrix something like in this way. So we just have this, which is 1 0, we just plug it here, and 2 minus 1 2 minus 2 1. This is how you make the C matrix, which is you take the eigenvectors and put it in the corresponding column of your matrix, and then you have the C matrix. So how do you find the inverse? In 2 dimensions, it's very easy to find the inverse. It's just you take the inverse is something like this. How do you do that? In 2 dimensions, you swap the diagonal entries. Since it's 1, it's no point in, even if it's swapped, you won't be able to distinguish. And we take the off diagonal elements and put a negative sign in front of it. That's why you don't have the 2's. You can of course follow other procedures, but this is the shortest way, which is swapping. Let me write it here. Swapping diagonal entries and negative sign in front of diagonal ones. Okay, now we are ready to construct our diagonal matrix corresponding to our matrix A, that is diagonalizing our matrix A. How do we do that? C inverse AC, and you can multiply these two first. So let's just put a bracket for convenience. If you multiply, you get something like this, and ultimately, so this is how you diagonalize a matrix corresponding. This is how you diagonalize a matrix A. But important, how do you check if your diagonalization is correct? Remember how we defined a diagonal matrix correspond in this scenario? That is, a diagonal matrix should have the eigenvalues as entries. So if you diagonalize a matrix, you must have your eigenvalues of the corresponding matrix as your entries. Here the eigenvalues are 2 and minus 1. So see, it's 2 and minus 1. In this way, you can diagonalize a matrix. So this sums up our review of linear algebra. These are the things we need to start our course. And in the next video, we'll start learning about something called Gaussian integrals and learn more about how to solve the Gaussian integral and things like that. Okay, thank you.